seen these problems before. Some of you might have seen this problem before. So if I cover some of these problems, I'm gonna ask, where do we start? If you've seen it before, give it some time before you answer. Okay, so how should we start here? What are we thinking? Like, how can we get information to start solving from? Yeah, Zach.
Well, we know that, like, let's say, like, the diameter of a tree is, like, we can define it by two nodes, right?
Mm-hmm.
We would get the correct answer if we can have P contain one of the nodes and Q contain another. So it might be possible to construct P and Q such that, like, we might not know the nodes, but we know that we're eventually one of them is going to cover that case.
Mm-hmm. Yeah, that's true.
So like maybe all pairs to be in separate sets at least one time. That would work.
Potentially,
May not be optimal.
but that's yeah.
Could be useful to recall like the standard algorithm for finding diameter on a tree.
Yeah. So how do we find the diameter on a tree normally?
You like start at a vertex and you BFS or DFS to find the most remote vertex from that, and then you do the same thing again. That first node is one endpoint of your diameter, and the furthest node from it is the other one.
Yeah. So okay. So normally, if we remember how we find the diameter in a tree, let's say we have a tree, and then we pick. Yeah. So we pick some node here. It can be any node. I think it can even be an intermediate node. And if we find the farthest node from this node, so let's say this one, for example, and then we find the farthest node from this one. So this or this, let's say that, our diameter of this tree is 4. How do we use this idea to solve this problem? Yeah.
So we pick one, like node. It doesn't matter. It's like one, like node 1 as like the starting point of the first DFS or DFS, and then you can use 7 or like 8 queries. The first query is the one node against every other node, just so that you know like what's the maximum distance, and then you can binary search to find the node which is farthest from like the starting node. And now that you know the node that's farthest from that starting node, you make your last query, which is that like farthest node and every other node, and it gives you the answer.
Yeah, so what you're saying is we're gonna start with node 1. Node 1 will be in set 1, so our 2 sets.
Yep.
So we start with this node and set A, and everything else goes in set B. 2, 3, 4, 5, 6, right? Let's say that. And if we ask this question, we will get back a distance, x. And then what's the next step?
So we can query A against, for example, the first half of B, and if the answer returned is x, then we know that there exists at least one node in that first half such that the distance is x. If the answer is less than x, then we know that the answer must be in the second half. We can continue that binary search over here.
Yeah, so just to repeat what he said, so everyone maybe hears it. If we query 1 with this first half, and the answer is x, then we know that there's a distance between the 1 and this set, that's x. If there isn't, then we know that the farthest node from 1 is in the second half here, right? And if we keep the sizes of these equal, then the number of steps is logarithmic. And then we find the farthest node from 1. What do we do after we find that node? Yeah.
You just query it against every node.
Yeah, we query it again against every other node. So let's say we converge on node 4 here. Then we check 4 with 1, 2, 3, 5, 6, and we check 4 with everyone, and that's our diameter of the tree. So this problem is solved. One comment, when testing interactive problems, some people, like Travis, might recommend you write a checker for them. And sometimes you have to, but it really, I don't know, like it takes a lot of time. So that's a problem. Testing interactive problems is kind of a problem. It's kind of a big endeavor.
Will they give you a checker?
No.
So they'll rarely give you a checker. Did you have a comment?
I was gonna say sometimes if you like write your program with like query methods, sometimes you can replace the code inside of the query method with something that actually like refers to an object that you've defined in your code.
Yeah.
So instead of like making a separate code to like do like the terminal interactive part, like that part would be like a pain in the ass.
Yeah.
I wanna avoid.
I usually do it by hand because it's usually faster.
That's good for like small cases for
sometimes
sure.
sometimes it's just really impossible to. Yeah.
Sorry, for the, like, I understand the solution to the problem, but as far as finding the diameter of a tree, you run the DFS once and find the furthest node, and you have to run it again?
Yeah. Yeah, because the first time you run it from a node, even if it's a leaf node, it's not guaranteed that that will be the diameter of the whole tree. Can you find like an example of that?
Well, if you have a long line and then one node coming off the middle, that's
Yeah.
the leaf node, then it would be
Yeah,
like
yeah,
half the
yeah.
diameter.
So then if you find the farthest node from that.
Yeah, I was just making sure, I
Yeah.
wasn't sure.
The visualization is you just take the tree, pick up one node and like dangle it with
Mhm.
gravity, and then you take the bottom node and you
And
pick
then
it up and
pick it up
dangle
with
with gravity, and then that's the answer.
I see.
Gravity moment.
And
As if there's a thing like called
But
gravity.
this problem, can't you do like the thing that Jacob's kind of talking about, like the binary bits and things, like you split up, you go for every bit and then split it up into two grids with that bit on and that bit off.
I think that's an equivalent
That's,
solution.
yeah, it's not quite equivalent, because you don't do the actual, you only need 7 queries instead of 9. You don't actually do the DFS simulation, but yeah.
Dude, but that's like the same thing. You're
Well,
just
it-
like querying them all ahead of time.
Yeah, it ends up being the same thing for the middle 7 queries, but you don't do the first and last.
But I think that would be like easier to type up though, right? Because you don't even need to do like any logic.
Yeah, but you have to do logic to build it back.
No, you
No,
don't.
because it's like the max of all the queries.
You don't-
Any
to
more
build back the
questions
tree.
on this problem?
You only have to print out the distance, right?
Yeah.
Okay.
So you just take the max of all
okay.
your answers.
Next problem is Serval and Snake. Ooh. This is an interactive problem.
Wow.
Now, Serval is a senior high school student in Japari Middle School. But on the way to school, he goes to a pond, and the pond has a snake. And the snake has a head and a tail. And he can walk over the snake here, as long as it's not walking over the head or the tail of the snake, because he will die. But thankfully, he can answer the following question. So the snake occupies the Z-Mayan grid, and the questions that he can answer are not where is the head, but it is given a box here, maybe some box like this. Then how many times does the snake intersect the bounding box? That's the question you can ask. Okay. And this is an n-by-n grid, and n is up to 1,000. You can see here. And because this problem was written in 2019, you have to make 2019 queries. So the point is, in this question, you need to find out where is the head and tail of the snake, and you need to do so in 219 queries. And the queries are, you can put a box, and what is the number of times we can each side? Anybody who hasn't spoken yet, maybe?
Like, I have a question about the problem.
Yeah.
What's the size of the snake?
The size of the snake is in the whole.
It always takes up the whole thing.
Yeah.
No,
it's
like,
like-
Space-filling snake.
That is
Oh,
1,000.
n is 1,000. But this is n by n.
Oh, so it's a guaranteed square.
Yeah, it is a square. Yeah. Yes. Tom.
So it seems like if for any query we have like an even number of things that leave our box, then we probably don't have a header tail.
Yeah. That's the main observation.
not
But they're-
necessary.
yeah, that's
Yeah,
not
you,
true.
you could have both.
That's not
Both
true.
the head
Yeah,
and
so,
tail.
but you know if you have both. So, to just develop a little bit more, like, you can look at the perimeter of the box, excluding the perimeter of the actual grid itself, and that's the number you would expect if it didn't have the header or the tail. Then every time it decreases by 1, it has a head or a tail.
Not necessarily.
No?
You could like run along the perimeter of the box and not intersect it at all.
Oh yeah, that's true.
People who have this
Yeah, so, but the first observation we find is that if the number of edges coming out is the number of intersecting edges that we get from our bounding blocks is even, then there is an even number of head and tail, so 0 or 2 in that box. The opposite of that is that if it's odd, then there is one head or one tail in that box. So we can start there, that's pretty good. Are there, so where do we go from there?
Well, similar to the other problem, we could do some sort of like, oh, we got an odd number, so we know there's something in this box. And then we can cut it up into pieces and figure out where it is.
Yeah, so we have to think about how are we gonna put our boxes, or like what kind of questions are we gonna ask? Yes, David.
So it's like 1,000, right?
Yeah.
So it's like, suppose we queried like every row and column, then like for all the rows, if we never find an odd, that means that they're both in the same row. And then that means that they can't also both be in the same column. And then now we have 19 queries to figure out which row it is.
Wait, what is the goal of this problem again?
Find the head and tail.
That's so
Fine.
funny. Yeah, find where the head and tail is.
Yeah.
Uh,
Because they can't.
So with the 90 queries, that'd be like a log for the rest.
Well,
yeah.
You can do every row and every column
If
and
you're
you have the
Yeah.
answer.
Well,
Yeah.
let's
No, you
so
don't.
let's summarize this idea. So let's start by first querying all the rows sequentially until we find in this row until we find like the odd rows, right? Until we find which rows are odd.
But
Well,
these
or
all
odd.
even. No, if you these are all even, you do have the answer. So we know that they're both in the same row.
These are
No, they're all.
yeah, this
They're all-
first one has 2, right?
Yeah.
This first one has or the second one has 1, 2, 3, 4.
Yeah.
And the last one has 2. So they're all even here. So we found that in these rows, none of them are odd, which means like they all have an even number of head and tail. Yeah.
Never mind, dumb question.
Okay. Yeah.
And so, since the head and tail have to be somewhere, they're in one of these even rows, so the head and the tail are both in the same row.
Yeah.
We can now say that.
So they're in the same row, but we don't know which row, right? So next is we're going to check all the columns. And what we know is, because their columns are we know because they're in the same row, they're on different or they could be in the same row, they are on different columns, right? So when we check all the columns, one of them is guaranteed to give us an odd answer. And these should be where the head and the tail are in these 2 columns. Yes, sir?
Like, I think I made like another observation. Well, something that you can do is if you query just one square, you can just check if it has a head or a tail in it.
Mm-hmm.
Yep.
Yeah, that's true. But the issue, we can't check every square. So we're trying to, but using this rows and columns thing, we have at least found a column and a row where the snake or the snake head and tail should be. So once we know, for example, in this, let's say in this column, we know there's a snake or head or the tail. Then what can we do once we have this column? Yeah.
We can query like for the column that we know either a head or a tail is in, we can query like half the column, and then if it's odd, then we know it's in like that half, and if it's even, we know it's in the other half.
Yeah.
And so we can do that in log for
Yeah.
each, the head and the tail.
Yeah, so we'll eventually come down if we keep querying halves. So for example here, if this is odd, we'll query, we know the head is somewhere in here. If it's not, then we know the head is somewhere in here. So this reduces down to a binary search at that point. And what's the number of queries we used in total?
2 2000?
2000 plus log.
Plus log.
Plus 2 log though, right? 'Cause you have
Plus
to do
2 log.
both
It's
logs.
pretty close.
Well, if they're in the same row,
Oh.
then you know the row for the other one, and if they're not, then you can do 4 queries to check like for.
Yeah, 4
Yeah.
queries, because,
Well, actually no, because as soon as you only 2, because you check 1. Actually.
so yeah, because you know they must be
Yeah.
different,
Yeah.
different, wait, you only need to do 1 query then, because
Yeah.
you know they must be in different rows and columns.
But I
So,
know.
like your 4 queries, like your 4 possible variations is like a square, but because you know there must be an opposite column, there must be one in the back and all.
Sounds like too much thinking. Might as well just do the binary search anyways.
So here, we find that this limit comes pretty close to what the actual limit of our answer should be, and this is usually a hint. We can start here. We can see that this is about twice 1,000, and see how we can work with that plus a little bit of log. It fits really neatly. You're like, oh, 2019 is 2019 back then, so you're like, oh, it's just whatever, but it is a hint. Now, at the same time, it can throw you off. They can give you a little bit more than you need, and it might look like something, but you can actually, for example, sometimes they might give you, I don't know, 1,000 queries, 2,000 queries, but you can do it in 10.
Yeah, like that one where they give you 9, you needed 2. First problem. What?
Which problem was that?
The first one, see.
Well, you needed
No,
7.
you needed.
Yeah.
You need 7 or 9 depending on your solution.
Yeah, in the first problem we needed to do a bunch of queries because we had to find, because it's not just like we need to find exactly what is the farthest node from node 1 first, and for doing that we did kind of a binary search, and use that node.
Any solutions work, and that's just 7.
Yeah, but it's still close to okay, how do we, can we think about, actually this is 2019 queries, can we think about how we can reduce this by almost half?
Can you guess like every other row and column?
Well, not exactly, because, I mean, if you do that, then let's say you don't find anything.
You do a
and
randomize.
things in the even parity room.
So, if you guess like you guess every row and column, well, if you guess every row, you don't need the last row, because like you can determine the integer from the bottom row. Probably do some like chaining stuff to remove some queries. Like we only need like 10 extra queries, right?
10 extra queries?
Yeah, like
Log 2 of 1,000 is 2.
Yeah. Yes, Jacob?
So suppose you query a bunch of random rectangles.
Random rectangles?
Not random, just random rows or columns.
Yes.
What are we at
Just
right
random
now?
rows and columns.
We're at
Just random rows and
2020, right?
columns.
If we did our same solution, but we didn't go sequentially. So when we check our rows, we check them in a random order.
Oh.
Then we would expect that it would take us about half the queries to find the answer.
That's only if it's not adaptive, right?
Yeah, if it's not adaptive. If it's adaptive, then they can wait until the very last moment to give you their
That'd be hard
That's
to
what
write
adaptive
though.
is.
Yeah, because it's like it has to be Hamiltonian. It's like
Yeah.
Yeah.
Yeah, it does tell you in the problem that it's not adaptive. So
Yeah. So
Yeah,
this,
like I
but in this
Well, it
case,
literally
because
says-
the snake,
Where does it say that?
it says
Does the
also note the
snake
snake
won't
is
move?
sleeping, so it won't move while severally using its device. And it does not depend on your queries.
yeah. But so in this case, if we check these rows in a random order first, then we can expect that our result will be a lot better. So if they gave us instead of 219, if they give us 1,500 or something, we will do randomized, which pass pretty safely there. As long as we check them in a random order. Yeah.
Our previous solution was using 2 times log base 2 plus 2,000, right?
2 to 2 to 2.
Yeah, but like,
I think that's not 2 times log base 2. It's just log base 2 because once it's in the same row.
You only need one binary stage.
okay.
Yeah, you only need one extra.
Since they're
So we were fine
opposite,
before,
you
right?
could just do one.
Yeah. But he's just saying that you could do one
Oh.
straight up.
Okay, are there any
We're
more
gonna
questions
solve
on that one?
Fix it.
Okay, let's move to this problem, point ordering. This is an interactive problem.
Yeah.
Oh!
This is a good problem.
We're given endpoints. The coordinates are big. No 3 points are collinear. The points are vertices of a convex polygon, but we don't know what polygon that is. Basically, the points, there's some permutation such that it forms a polygon. And that's what we're guaranteed. And we're given the number of points, n, but we don't know the coordinates. And we need to guess the permutation by asking some queries. In each query, we give these 4 integers, and there's 2 types. So type 1 query, we're given the area of the triangle formed by the 3 points that we pass in. And query of type 2, we get the sign of the cross product of the 2 vectors between the I point and the j point, and the I point and the q point. So if we visualize ijk, so they form this triangle, and we would get the sign of the cross product between the vector I to j and I to k. So these are the 2 query types that we can do. And we need to find the order of the points, I think. Yeah, we need to find the order of the points. We need to print them in counterclockwise order. And we need to do so in 3n queries. Okay?
Is t equals 1 not just like the actual value of the cross product?
It's the absolute value.
Yeah. Yeah, so we can get either the absolute value of the cross product or the sign, but we need to use 2 queries for that. And is the problem clear?
Wait, so we have to sort this in like linear time, basically.
Yeah,
Yeah.
you need to give them the order of them in a counterclockwise order. So how can we get started with this one? Yes.
Well, if we can find a way to get like, if we just take a single point, we know that like the order of the polygon counterclockwise will be the same as the order of the angles between that point and each of the other points, right? Because it's a convex polygon.
If we take a point and what?
And just let's say measure its angle compared to all other points, right? Then that sorted order is the same as the order of the polygon, right?
Yeah, but we need 3 like we need a reference point because they're all like in space. So I can't do an angle between 2 points immediately. I need the intermediate one, right?
Yeah. No, but I'm just saying if we can get that,
Oh.
like that would give us an answer.
Yeah.
Because the polygon is complex. So
We just drop an origin at like -10 to 10 to
Well, yeah, but we can only query with the points given to us. So we can't have
Oh,
the point.
yeah, true.
Yes, Sam?
So if you fix like one pair and then you queried like the area, then like because like triangle area is like base times height, then that would give you like distance from that line. But then the sign would give you like the side of it. So there's like, it's a little weird.
Okay, let's start with that. Let's fix 2 points, just 2 arbitrary points, and query the area with all the other points. That should give us a number. This is the area, and to visualize what we're getting here is that if we start with like this, then the largest number is going to be the the farthest point from our line, right? So let's start with that. So let's say we get this point down here.
But we don't know the 2 points that we chose are right next to each other, right?
We don't.
They don't have to be.
Yeah. Yeah. This could have been a different point. It would still be the farthest point from that line segment that we got. Yeah.
Can we not use this technique similar to like the tree to find like 2 points that are opposite each other?
Yeah.
I don't know if that's useful though, now that I think about it.
It's similar. It's similar.
Oh, and then you can probably, so you'd be, like, using that, you can, like, split the polygons in half by taking the sine of the cross product relative to, like, that diameter.
Yeah.
And then you'd also be able to get, like, another 2 points by using the same technique with the magnitudes, and then you might be able to split it over and over again until you get the exact order.
Mm-hmm. Yeah, I think you're exactly on the right track.
Yeah, that's so it's like the 3n is the sum of all the hours of 2 up to n. Yeah, because like said it right.
Well, Jacob, did you have something to say?
No, I'm just gonna use too many queries.
Oh yeah, because you don't know that you're splitting it in half.
No, you
Yeah.
do.
So okay. So can you explain again?
Oh, wait, no, you don't, yeah.
'Cause we
you
said
could-
we're-
you could get unlucky.
Yeah, because the polygon might have, like, clusters of points that are super close to each other.
Yeah, or like you just pick a bad pivot on unlucky.
Well, it's 'cause like the first thing that we did was we like fixed a pair, and we don't know that pair is like opposite
Yeah.
Yeah,
sides
but
of
I'm
the
saying the
polygon.
opposite of that opposite, like some to diameter, but now that I think about it, that might not necessarily work.
Yeah, we already used most of our queries.
Yeah. So we already used them in queries. Yeah. Yes.
So I think if you fix fix a pair and then do all the areas and then do all the signs, then you get like for every point like which side it's on and then how far it is from that line.
Mhm.
And so now because the polygon's convex, you have like a bunch of pairs that gave you the same result, right? Like you have like a bunch of pairs that like gave you the same triangle area and like side. But you can only have like 2 things, and so now you have n queries to resolve like which side each of those guys are on.
So with which line are we using? Is it this one or?
Yeah, just like fix any pair, and then now it's like we're splitting everything. Like we know like every point is either like on the left side of the line or on like the right side of the line,
Mhm.
right? And then now you know every point, like you know its distance from that line, right? But because the polygon is convex, you can't have more than 2 points that are on the same side of the line be the same distance from the line.
Because also no is very collinear, so.
Yeah. So now we have like all of these things, and so we know it's going to be like increasing distance and then decreasing distance. But since like we might have like we don't know the order of like them, right? But we know like basically we're gonna pick like something that's really close to the line. Like it's kind of like a merge sort, and so we have n queries to resolve like what thing are we gonna take.
If you had like 4n, then you could just like split it in half twice.
Just to sort of like restate that, like if you fix your 2 points and then you use 2 n queries to put every point on one of the sides and also figure out how far it is from the line on that side, like Saba was saying, then you can do sine queries from the maximum point, and you can figure out for each of the other points that are on that side which side of the maximum that point lies on. So like once you know your most extreme point, you can then query from that to like one of your source points and figure out, oh, is this like to the left of my maximum or is it like to the right of my maximum? And then you have like 4 quadrants basically that when you sort and concatenate them, you'll have reproduce the answer.
Nice. Could you do the same thing between the both of the maxima on either side, or probably not? Oh, you could.
I guess if you made one of your like once you find the maximum points, you make that vector your
Yeah.
direction. Yeah, you can do that. Well,
So it's like increasing, then decreasing, then increasing, then decreasing.
Yeah.
That's cool. So it's n.
But I imagine there's like
n,
different
yeah,
solutions to this.
Okay. Yeah. So does anyone have any questions? Did they understand the solution? I think Jacob explained it pretty well. Or do you want me? Did I need to repeat it?
Are you doing an example?
Yeah, sure. So let's. I guess we have a polygon here.
That's a polygon.
That's a polygon.
Achieving convex.
Polygon is literally convex.
now that's convex.
So first we pick some 2 points and we find all the we query all the things to find the farthest point. So let's say we pick these 2, and we find the farthest one. And this one. Next is we're given areas. If we find the how does it work here?
So can you?
5 and 3 would be
can you
good.
move the thing back down? We can't see that.
Oh,
thing
sorry.
anymore. So you query for every point that's not A3 or A2. You query the area and sign of the triangle from A3 to A2 to that point.
Yeah.
So now you have the distance from the line to A3, like from the line between A3
Oh,
and
yeah,
A3, and the side. So for example, A4 is going to be negative, and A1's 5 and 6 are going to be positive. And then the problem is, like, okay, if you look at the bottom half, it's like trivial because there's only 1 point. But if you look at the top half, there's 3 points, but you don't actually know what order they're in necessarily because like the distance from the line doesn't actually tell you what order they're in. But you know that the maximum point is like you can fix that point. So now if you query between A5 and A3, you know which points are are between A3 and the max. And so now you know, because it's convex, the distance from the line to A3 and A2 must be strictly increasing up until you hit the max, and then once you hit the max, it must be strictly decreasing. And so you can figure out now every point you know which side of it on the max it is, and so you can sort those heights in each quadrant between A3, A5, A5, A2, A2, and its bottom. Like you have to do the same thing on the bottom. It's like A4 and then A4 to A3.
Does that not use 4 n queries?
Uses 3 n queries.
Yeah. So this
Is-
first time we queried. We only query area between A3, A2, and everything else.
You said area and sign.
Yeah, so that's 2n. And then
Yeah.
for everything on the top half, it gets 1 more query as the third point between itself, the max, and which quadrant it's in. And so the sum of that is like, whatever. And then you do the same thing for the bottom. So every point that's not A3 or A2 gets 1 query, or A3, A2, or the max, or the other max on either side.
An area query?
No, it does not get an area query because you don't care about the area, you only care about the sign.
Okay.
You know, like the area of A3, A2, and some other point must be strictly increasing up till the max and then strictly decreasing from the
Oh, I
max.
see. Okay, got it.
But the max isn't necessarily unique. Like there might be 2 things that are the same distance for the line.
That does work though.
But it's like,
Because you can pick an arbitrary one,
Yeah.
and it will say like the other one is on the other side, and well, they can't be 3 because they'll be collinear.
yeah.
And if there's 2, it'd be
Yeah.
like. pick
You'll
one of
you'll
the
put it on the
ones.
right side.
To be right
Like
next
if you
to
pick the one on the right, then you'll know the left's on the left, and then vice versa.
So like,
'Cause I was thinking
So you have to
about-
store the area queries in the first time and use it.
That other max would either be the largest of like the increasing set before you hit the max, or it would be the largest of the decreasing set after you hit the max.
Why does it take 2 n queries in the first pass? Because we're doing both types of
Area and
queries.
sign.
Oh yeah. Okay. Let's do one more.
One more. One more
Let's
time.
do one more. Okay, this one has 2 solutions.
You have to find one.
You have to find one. Okay, this problem we're given again
Was
a
that
tree.
funny?
Where-
Yes, it was.
I know.
And it's rooted at node 1. Okay, a tree is a connected graph of those cycles. We choose a hidden node, and we need to find the node. There's 2 types of queries. we can say, what's the distance between node U and this hidden node X? And we can say, what's the second node on the path from U to X? And U must be an ancestor of X, if not, you get wrong answer.
Dang.
Yeah. So for example, we know safely that we can do S query from 1. And that will give us the second node on the path from 1 to X, because 1 is the root, and so it is an ancestor. We need to find
Wait, I
X.
thought ancestor was like the other way. No?
Ancestor is parent. So
Oh, on the path from X to U. Okay.
So is that like the child towards X from U?
yeah, it's the child towards X, basically. We need to find X in no more than 36 squares.
Oh, right.
The hidden node is fixed in each test beforehand and does not depend on your queries, because otherwise they can just hide forever, almost. So how do we get started with this? So there's 2 times 10 to 50 nodes in the whole tree. It's quite a big tree. We are given the tree.
Oh, so you do have the tree. Okay.
We have the tree this time.
And it's okay. So it's not weighted, right? It's like an unweighted tree.
What would the weight?
Oh,
for the path.
yeah.
Oh.
Yeah, it's not weighted.
I think that's
So what happens if we ask a D query from the root? What happens? Yes, sir?
Oh, we figure out like what multiple it's on.
Yeah, we find the
Depth,
depth.
yeah.
Yeah. What happens if we find an S? We do an S query from the root.
Well, that'll tell us which subtree it's in.
Can't you just do like query 1 and query 2? Oh, wait, never mind. It could be like usual.
Oh wait, so I wonder what's the
Yeah. Wait, so
we know what subtree
Highly
it's in,
likely don't.
then we could like also figure out how far
About
different
how far
subtree we can go.
Or we know how we're into the subtree, so if we just do a single D query from
Yeah. If we look at this bound, it looks like 2 times 18.
True.
Right.
And also
And the 18 looks like about log of n.
No.
And 2 looks like these 2. So let's look at along these lines. But yeah, the thing is like so let's just start with the
Bless you.
D query from the root, so we can find the depth of X. Okay. Yeah.
Oh, nice.
If you like take a node and so let's say you already know this D query, so you know the depth of the node, right?
Yeah.
If you take a random node and take its D query, if it's greater than the difference in depth, then you know it's not a parent of.
It's on the path.
Yeah, it's not on the path,
Yeah.
right?
Yeah. Yeah, so instead of a random node, let's try to pick a meaningful node. So what's a meaningful node for a tree? Yeah.
Since we like have access to the whole tree, I'm just like spitballing. I don't know the solution, but like, can we like pick a node? What like if we get the distance from the root 1, can we just like pick a random node, or not random? Sorry, pick a node that's that distance from node 1, and one that specifically like would like split the other options in half, where like based on that like the distance we get from that node, it's like tells us on like which side of the tree.
Yeah, so we need to split the tree in half. So what node is that?
Centroid.
It's a centroid. So if we pick a node, so for example, let's just to get started, start with the root, and I don't know, let's suppose we have this tree here. Something like this, I don't know. And we find B, we find X, and we say, okay, we find B to X from this root. let's say we wanna cancel. We wanna see what subtree is in. So let's say it's in this subtree on the right. So we can just delete everything here.
Oh,
So,
and then
let's start here.
Sort of relying
So finding the centroid in this
Imposter
tree. The centroid, remember the definition of the centroid? Is a node where the sizes of all subtrees are n/2 or less. That's the definition of a centroid. Because once we look at the centroid, for example, and we query here, if we do an S query from this centroid, then we will be able to kind of cut out more than half the tree if the centroid is an ancestor.
Yeah, so, but how do we know that it's an
Yeah, so we
You
need
can
to
check if it's using a dequery like Zach said earlier, I think.
Yeah. So what Zach said earlier is that if the distance from the root to the centroid and plus the distance from the, or sorry, if so what we need to do to check if it's an ancestor, let's say is U an ancestor of X. So distance from root to U plus distance from U to X should be equal to distance from root to X.
Oh, sure. And if it's not, then it's a bug.
And if it's not, then yeah.
So like you do that, you query if the centroid is an ancestor of X, and if it's not, then you cut out its subtree, and then you just recompute the centroid on this like smaller tree now.
Exactly. So what we do here is we find the centroid in this tree. If it is an ancestor of X, then we can do a simple S query, and we cut out everything other than the subtree, and we redo it again. Otherwise, we cut the centroid out. Like let's say X is somewhere up here in this subtree. So otherwise, we can cut out the centroid and recalculate on this tree again. Find the centroid, repeat.
And are we like ignoring nodes less than that are deeper than the depth of X?
Dang, that tree was pretty sucks.
Deeper than the depth of X.
Because you know what the depth of X is, right?
That's smart.
You can. I don't even think you have to though.
Yeah, cut out everything deeper than the
And there's
depth.
like 1,000 nodes.
There's
You don't need to, 'cause
100
it's
dozen.
just-
Oh,
Understood.
okay.
Yeah.
So
But this is
but we can do like naive centroid and be fine. 36.
well, because yeah, like the number of operations, the number of times we do this is logarithmic.
Right.
So we can do a linear time.
And like it's even better than that though, because it's like you're dividing it in half every time.
True.
Yeah.
So it's like it's really order n in total.
Wait, how do we output
that's
that?
true,
We
order
just
n.
have to do a distance
I mean,
query.
like, it was order n anyway, but,
Returns
like,
zero X.
But now it's
But
order
now it's
really
really
order.
That'll work.
Okay, and the exclamation mark is not a query itself. Like
It's an answer.
you tell them the system your answer.
Yeah. So doing this, we will find answer.
What if so if there's two centroids, we choose one arbitrarily?
They do not matter.
They do not matter.
Yeah. Alright, Jacob, do you think you can go over your problem in 10 minutes?
Is that how long we have?
Yeah.
I can talk about it in 10 minutes.
Oh baby.
No.
Is this
Alright, next we will give it to Jacob. He has solved a problem yesterday that really inspired him, and he wanted to show it to you all.
Yeah.
So here I
Let's give it up for Jacob.
You guys. Eularian?
Yeah, Eularian. So here we've got a interactive problem.
Yeah. Oh, perfect.
So
Definitely.
this is kind of like another archetype of interactive problems where you're told that the interactive, like it's one of the ones where it's not adaptive. So it tells you that the graph is fixed. But first, what is the problem? Okay, so the interactor has hidden in secret a graph, an undirected graph, simple graph. It's connected, no multiple edges or self loops. And your goal is to figure out whether or not the graph is Eulerian. And so first we'll recall that, like, what's the condition? Can someone tell me like what the condition is for a graph to be Eulerian? Yeah.
Connected and no odd degree.
Isn't this problem very similar to the snake problem?
Yeah. But also no odd degrees.
Yeah, it is pretty similar. Like, oh, yeah. Oh,
Huh.
yeah.
I know it said it was connected, but
It is.
ALL even?
all even. Oh. No odd.
Right.
No, it's a
So
10 to
that's-
the 18 even number.
And so the query that we get to ask is, like, we give the interactor a set of vertices, and it tells us the number of edges from G, which have both of their endpoints in the subset that we queried. So, for example, if we were to query like the entire set, like all numbers 1 through n, we would get the total number of edges in the graph. We query like a single vertex. We're not going to get any edges back. We query 2 vertices. We'll just get 1 if there's like an edge between them. So that's the question that we get to ask, and our goal is to figure out if the graph is Eulerian. Or what we're going to be figuring out is whether
What is Eulerian?
it means that there is a path that uses every edge exactly once in the graph. Starts and ends at the same place. So like, something like this.
I thought it contained no loops.
It contains no self loops,
Oh.
which means there's no edges that are like going to themselves.
None of it matters.
I guess it
Yeah, not that it really matters, but yeah. So, number of nodes is up to 10 to the 4th, and number of edges in the hidden graph, so like the answer is up to 10 to the 5th. So, one of the things that we can do, or does anybody have like any ideas before I just kind of like say the solution because there's not that much time? Something we could, something we could do that could tell us that it's false. If I can, yeah, go ahead.
I think there has to be a relationship between like the number of vertices and the number of edges, because there's no self loops. But I'm not like, I'm trying to think. So there's no self loops, so you won't have the weird things.
There's not really any other restrictions on what the graph looks like. We could have a tree. We could have a complete graph. We could have.
Yeah, but like if it's a tree, then we instantly know it's not possible.
But you don't know that it's a
you don't
tree.
know it's a
Yeah,
tree.
but like let's say we query the entire graph. There is a subset of answers that we can immediately say, oh, that's not possible.
Sure, if we query the whole graph with n vertices and we get n minus 1 back as an answer, then we can say it's a tree. But there isn't really, but like, say the answer is n. Like we don't know if it's a cycle or if it's some sort of like a pseudo
But
tree.
if it's n plus 1, then that also feels impossible. That also.
And you can have like a cycle.
That's, yeah.
And and this one might also be impossible.
I
So
feel like there's a non-trivial subset where it's impossible, and then you can do something with that.
Well, but like also no, I guess it's connected.
were you gonna say something, Jacob?
No, it's, yeah.
So let's just say like as a first step, let's query everything and figure out the number of edges in the graph because that seems like it might be useful for us to have. Now, a condition of graph being Eulerian is that if you split if you split all the vertices into 2 groups, you should be able, similar to the like what we were talking about with the snake. Since our Eulerian path has to use every edge exactly once, and it's going to be a cycle, or it's like Eulerian cycle, if we start at some vertex, we're going to have to cross over to the other set of vertices and back an even number of times in total if we're going to use all the edges. Do we agree?
True.
True, so true.
So if
So
we
we're-
were, say, to split all the vertices into two groups and query how many edges are in this left subset and how many edges are within this right subset, we can then use like the total that we found originally minus the query over set A and the query over set B to figure out how many edges are going between those two sets. Yeah.
So then we can do that thing that we talked about earlier, like the first problem, where you like binary masks so that they're always on, they're like for every pair they're always on different sides, and then figure that out, right?
You know, that does work. That does work, right?
Wait, what? I wasn't paying
Wait,
attention.
so
So like you can set up the binary mask thing like we talked about for the first problem, such that every pair of nodes is always on a different
That's
set
what I
of
was
leaves.
telling you last night.
That is what you were telling me last night. That is what you were telling me last night.
And then,
But
yeah.
if you're,
I haven't submitted it, but
Huh?
I think it works, but I haven't submitted it.
Yeah.
And also, you want to shuffle the nodes because you can construct a graph that will fail.
So because the interactor is not adaptive and the judge is not secretly changing the graph to try and make it so that you don't discover that the graph's not Eulerian, what we can do is randomly split the nodes into these two groups and then make this query. And if we do that, we can do that a total of 29 times with the queries that we have remaining. And if we think about how, like, if all of the vertices are even, then regardless of how we split them, we should always find that we have an even number of edges between the two groups that we split into. But if there is, if there are any odd vertices, what you can think about is like, sort of like hold on to a single odd vertex, and then randomly assign all of the other vertices to the two groups. Now, the sum of the degrees inside of each of these sides is going, the parity of the sum of the degrees on one of these sides is going to equal the parity of the edges that are going between them. Which is to say that every edge that goes between two vertices in one side is going to contribute to the degree sum 2 times. And any odd vertex is any edge that goes between these two is going to increase the degree sum by 2 on that side, and any edge that goes between both sides is going to increase the degree sum by 1 on each side. So if there's an even number of edges going between both sides, then the degree sum on both sides should be even, because the only edge types that we have are ones that stay on a side or pairs that go across both of them.
So that's like considering edges between odd nodes?
That's like all of the edges, regardless of the actual degrees of the vertices. Edges that go between a side don't alter the parity, and edges that go between both sides should come in pairs if everything is going to be even.
I have an analogy.
Yeah.
So imagine the odd degree nodes are like ants walking around on a table, and you've got 2 cups, and you go bam, bam. You need to make sure that every time you put down the cups, there has to be an even number of ants in both cups.
Yeah.
And if that's ever false, then you find it. And then you're just putting the
what are
cups
the
on.
odds?
Yeah. That's like the
Yeah, 'cause the idea is that if you have an odd number of vertices on one side, well, first of all, in a graph, you have to have, a graph can't have an odd number of odd vertices, because then
handshaking lemma.
yeah, because
Also, the sum of 2
because if you start with no vertices, each edge you add is going to flip the parity of 2 nodes. So you start with no odd nodes at each, yeah.
No, wait, well, no.
Yeah, every edge that you add or remove from a graph alters the parity of two vertices. So we have to have an even number of odd vertices and an even number of even vertices. Or, I guess, that doesn't quite seem right.
That's not true, but like, yeah, the sum of
It
degrees
has to
is always
match-
even
it
because
has to equal.
drawing an edge increases the degree of the graph by 2,
Wait
which is
till-
0.
Wait till you hear about a graph with 3 nodes.
So what I'm saying is that if you,
getting it each time.
if you split into two groups
Oh,
and you have
also you only have 1 cup in your analogy, not 2.
What?
Because all the remaining.
and we have like an even number, if these red nodes denote the odd vertices that we're trying to find with this process, because if we find an odd vertex, we can say, we can report that it's not Eulerian. If there's an even number of them on both sides, it's possible that they are like paired up with each other within these sides. But if we have an odd number of odds on one of the sides, we know that one of those connections is going to have to come through here. And so what I was saying about fixing one of the odds is that if we just kind of look at one ant or one odd vertex, and we look at the state of all of the other ants, which are being like randomly assigned to a side, because this process of splitting them into two groups is basically go over all the numbers from 1 to n, and then just basically flip a coin to assign it to one of the sides. If we look at this vertex last, there's a 1/2 probability that it lands on the side that makes the parity even, and there's a 1/2 probability that it lands on the side that makes the parity odd. And that same argument holds for all of the other odd vertices. And so from that, you can infer that the probability of finding this, or like the probability of this, like vertex, either hiding from you or like being found in some iteration, is 1/2.
And you do it 29 times.
And you do it 29 times.
Pretty big deal.
So the likelihood that it hides from you 29 times is going to be 1/2 to the 29.
Some sneaky ants.
Yeah, which is, and basically because the interactor is not adaptive, we can use this like reasonably high degree of certainty as like enough, like sufficient to solve the problem. Like, Say what? We have 60 queries. Our first one, we got the total number of edges in the graph, and then we just do we do pairs of queries, splitting them into two groups, and getting the number between them, and we do that 29 more times. There's one type of query, but for each iteration here, we need the number, because remember what our query was the total number of edges within a set that we gave the judge. So we're going to split into two groups A and B, query this set A, query this set B, and then take this difference to be the number between sets A and B.
And then, just for fun, you have one query left, so do with it what you might.
Yeah, we have one query left. Sure, exactly.
Query the
Does this make
entire
sense?
graph.
Again.
This idea of like querying stuff and trying to figure out
Maybe
how
change.
certain you can be that you'll find the answer is something that is useful for non-adaptive problems.
I have a question.
Yes.
That is more in general, and it's to both of you to comment. If you send, in your experience, if you send in a submission on an interactive problem, and your program crashes, and you would say that a typical problem you would get runtime error. Do you find you get runtime error, or are you given a different response?
I don't usually make bugs like that.
That's fine. That's fine.
Like sometimes the interactor is bad and it tells you wrong answer no matter what. Like it should give you runtime error if you ask it the question.
Just don't write bad code.
What the verdict you get on an interactive problem should just be like, something's wrong.
Sometimes it will tell you in the spec that if you make a malformed query or you use too many queries or something, like on the first query that exceeds your number of queries, it will report back something like -1, or it'll like send back some flag that's supposed to indicate, okay, your program has screwed up and you should now, it generally uses the phrase like terminate gracefully, you should just like exit your program, and the judge will like,
And then the judge can give you like a.
and then the judge can give you, the judge can give you a verdict that actually corresponds to what your program did.
I
Yeah.
never do that though.
If you don't do that, then you can get like time limit
then
exceeded
you
or
get
islands
whatever.
limit exceeded.
Yeah.
That can be pretty annoying.
I feel like on interactive problems, you either AC or you don't AC, and that's the verdict that you get.
That is what happens with most problems.
We should remove all other
Yeah,
verdicts.
It's like I feel like the
How do you
verdicts
make a
on
vote?
interactive problems. I don't know. I never really.
Usually.
They're definitely
The
are
the relevance of the question is
We like
not
to
so
use
much
our
from a contestant viewpoint, or from an authoring
Or will it just wrong
of
answer?
systems.
No, it doesn't. I think
For example, I would text
yeah,
right
Ace's
now,
wrong answer.
the honor code is smarter, it will be.
What
Hey,
happens?
hey, we're not done yet. Sit down.
Can this conversation happen elsewhere though? Is there people who are hungry for lunch?
Well, you can go to lunch when we release you for lunch.
I'm back in
When you release for lunch?
All right, everybody, please thank Sharon and Jacob.